Friends, welcome to follow up. Let's have a look at problem 2845, count interesting subarrays. In this video, we're going to explain how to use data structure to solve problems and how to reduce the problem to a known problem. So here we are given an zero indexed integer array called nums and an integer modulo and another integer key. So our task is to find the count of subarrays that are interesting. So the definition of interesting subarray is the following. So let's assume this is a subarray starting from index L and ending at index R, right? So we want to count the corresponding indices which corresponding to numbers modulo this number modulo equals key, right? Then if the count of such indices still equals to key in the sense of modulo the constant modulo, then it's called interesting subarray, right? So here we want to return an integer denoting the count of interesting subarrays, right? So here are two examples. So in the first example, if you compute the numbers modulo 2, we get 1, 0, 0, right? And then, so we can start from index 0, ending at index 0, and ending at index 1, ending at index 2. So there are three such arrays. So we're going to return 3 for example 1. Well, for example 2, you can do the modulo. So 3 modulo 3 will be 0, this will be 1, this will be 0, this will be 0. Then you do the counting, and the output is 2. So here the constraints are the following. First, the length can be as long as 10 to the power 5, right? So a typical computer can treat 10 to the power 7 operations in a second. So this one basically tells us we need to use time efficient algorithm. So the second one is on the range of the elements in the nums. So they are all positive integers, and also the modulo is positive integers. So here key can be 0, but it's less than modulo, as it should be. So with that said, we are ready to analyze the problem. So here the strategy is to use data structure to solve the problem. So here I'm going to use the dictionary abstract data type. So basically this is a hash map, right? So another thing we want to demonstrate is to reduce the problem to a known problem. So let's first comment that this problem can be reduced to problems such as find number of subarrays with a given sum, or find number of subarrays with sums divisible by a given integer, right? So they are actually the same. So let's look at the code, and in between we are going to explain the logic. So first we want to do the counting, right? So we want to do the count for the numbers which modulo this number equals the given key, right? So basically it's either a yes or no, right? So we are going to have a binary array yield from this logic. So though we don't need to explicitly compute out, but in order to explain the idea clearly, I'm going to compute this one using the list comprehension. So reduction of the nums list. So here we are going to use list comprehension. So let's still use the nums as a name. So basically we want to check the number modulo this modulo equals key, right? Let's use 0 and 1. So here I'm going to use integer, right? We change this logical judgment to 0 and 1. Then for y in nums. So this way we change this nums to be 0 and 1, right? Then the problem is reduced to the following. So we just need to count subarrays such that, so the sum with, let's see, with sum s, such that, so s, we want to count such subarrays s modulo this modulo equals key, right? So this is actually a very straightforward problem. Especially you can look at this kind of problem in the LeetCode or in just the daily practices. So what we want to do is to use a dictionary to count, right? So here let's initialize a dictionary. So here we are going to the dictionary, we are going to store the remainder and its count or frequency. So let's initialize with 0, so its count is 1. Let's count that 0 appears once. So then what we want to do is that let's also initialize a result variable. So the result, it will be the count. We are going to return its final state. And also we are going to use a current. So the current essentially compute the sum from the beginning up to the current index. And this sum, for this problem, we are going to compute the sum in the sense of modulo, this number modulo, right? Then this is the basic, very simple for loop. So for y in nums, right? So notice that y is either 0 or 1. Then we're going to compute the current equals 1, right? So then we can compute the remainder. The remainder is nothing but this modulo this constant, right? So this is the remainder if we add all the elements from the very beginning up to the current index I, right? So from the beginning up to index I, both inclusive. And then we want to check, right, if let's assume R is greater than K, if this remainder is in the dictionary. If it's in the dictionary, it means that for some index I0, for indices I0, because this K can appear multiple times or have a frequency larger than 1. For this indices K0, it means that from index 0 to up to index I0, right, the corresponding remainder will be R minus K, right? Then if we do the difference of the current sum minus the sum up to index 0, so we know that, so this basically means from index I0 plus 1 up to the current index I, so this sum will have remainder K, right? So this is the logic. So let me put this in the tail, right? So now what we want to do, this check. But notice that it's possible that this R is less than the K, right? For example, let's use an example. You have a K equals 3, and let's see, the number equals 5. Right? Let's see. Modulo equals 5, and then we're going to do 21, right? So if we do 21, so modulo 5, that's going to be 1, right? So 1 is less than 5. But in this dictionary, we store remainders. So in other words, we want to store 0, 1, up to modulo minus 1. So in this case, actually, we can borrow 1 from this. So we are going to change to, let's see, 21 minus 5, right? So we bring a 5. So in this case, we are going to count this as 6, right? Bring 1 copy of modulo. So this is actually some mathematical detail you need to digest. So with that said, we are ready to do the counting. If R is greater than or equal to K, so basically we can check the frequency of R minus K, right? So let's write the code and then explain. So we are going to count this. So so we want to get this K, R minus K. So if this K is not in the dictionary, so it means that there's no subarrays ending at the current index with the no interesting subarray ending at this index. So we are going to get this 0, right? So this is one. Another case is if R is less than K. So it's actually this case. So we're going to check the remainder for R plus a modulo, right? minus key, and then we use 0 if this key does not in the dictionary. Notice that the current, if we regard the current as the sum, and the keys corresponding to a previous sum, the current sum is greater than or equal to the previous sums, and then we can always do this, borrow one. And so I guess this if else block is might be the main starting point for some people. So now after this, no matter what we do, so we are going to add this remainder information to the dictionary and then continue. So let's get the frequency count for this remainder, and then we add the current one. So this is the add one, right? So afterwards, so we just need to return the result state. So this will be a solution for this problem. So actually here we used this reduction of the numbed list, but in practice you just don't need to do this, because this uses an ON space. You just need to do the current add y. We just add this part each time. We add this part, so we don't need to use this space. But for clarity, we did this reduction. Now, before any further comments, let's first do a test. Yeah, it passes one test case. Now let's look at the generic case. Yeah, it passes all the generic cases. So here I would comment that once you digest the logic of the problem or practiced a lot of such kind of problems, then basically the code for this problem is just a for loop with the aid of hash map or dictionary. So with that said, that's about it for this video. Thank you.